in rectangular waveguide working on TE10 mode. So here our rectangular waveguide is given an input formation in terms of TE10 mode, and the frequency that I am giving input is the microwave frequency. So let us study the microwave test bench first. Say from the gun power supply, we are giving input to the gun oscillator. Over here, the voltage is given from the power supply. Once the voltage exceeds the threshold voltage, my gun diode goes in a negative resistance region. Once the gun diode goes in a negative resistance region, it works as an oscillator. So here, microwave frequencies are generated by the gun diode in a gun oscillator. So this is a source of microwave frequency. So between source and all the loads, I am putting one isolator. The reason to avoid damage of my gun diode. If the reflected signals came back, જો અહીંયાથી લોડ માંથી reflected signals પાછી આવે તો chances છે કે મારો gun diode damage થઈ જાય. એટલે માટે હું શું કરું છું, one way communication રાખું છું. અને one way communication કરવા માટે મારે શું કરવું પડે તો કે isolator. That means power will move from gun diode to the pin modulator, but reverse is not possible. That means from pin modulator to the gun oscillator, power will never came back. So I'm using one isolator over here. Thereafter, pin modulator. Here, two signals are coming. One is the information signal and another signal is my carrier signal, that is microwave frequency signal. Here, a modulation of the information and carrier signal occurs inside a pin diode and it acts as a modulator. So here the modulated signal is generated. This modulated signal is given to the variable attenuator, but at present I am keeping variable attenuator value as 0. This means 0 value no meaning શું છે તો કે જેટલી પણ સિગ્નલ ઇનપુટમાં આપી છે એટલી જ સિગ્નલ મને આઉટપુટમાં જોવા મળશે. અત્યારે વેરિયેબલ એટેન્યુએટરની વેલ્યુ કેટલી રાખી છે 0 dB attenuation. 0 dB attenuation means whatever the signal I am giving from pin modulator, the same output I am getting as a output from the variable attenuator. That means none of the signal gets attenuated. In this frequency meter, we are measuring the frequency generated by the gun oscillator. એટલે આજના પ્રેક્ટિકલમાં આપણે શું કરવાનું છે, આજના પ્રેક્ટિકલમાં આપણે મેઝર કરવાની છે ફ્રીક્વન્સી, ઓકે, અથવા તો વેવલેન્થ. કઈ ફ્રીક્વન્સી ને કઈ વેવલેન્થ તો કે જે ગન ડાયોડે ગન ઓસિલેટરે અહીંયાથી જનરેટ કરી છે એ આપણે બે મેથડથી ફાઇન્ડ આઉટ કરશું. વન યુઝિંગ ધ ફ્રીક્વન્સી મીટર and another using the slotted section. We will find out the frequency by using two methods, one using frequency meter and another using the slotted section. So let us start our experiment. I am sharing one video with you all. Wait for 1 minute, I am sharing it. Are you all, can you be able to see the video? Can you be able to see the video file, students?
Yes, ma'am.
Yes, ma'am.
Okay,
Yes, ma'am.
I'm running this video. Just check this out. Hello. Today we are going to perform experiment number 3. That is to determine the frequency and wavelength in rectangular waveguide working on TE10. So we know about rectangular waveguide. This is its broader dimension and this is its narrower dimension. So first of all, let us calculate the broader dimension as well as the narrower dimensions of the rectangular waveguide available in our laboratory. So we are going to calculate its value, this value as well as this value. So let us calculate these values. Let me put a scale over here. The the value is 2.4 centimeter. So I'm writing it over here. The value for the broader dimension is 2.4 centimeter. Please note down this value in your notebook. Please note down this value in your notebook, students. Have you noted down?
Yes, ma'am.
Yes, ma'am. That's right.
Okay. Similarly, we will calculate the value for the narrow dimension. The value for that is 1.1 centimeter. So I am writing it over here as 1.1 centimeter. Please note down this value also. B is equal to 1.1 centimeter. So this is the rectangular waveguide available in our laboratory. Now this rectangular waveguide we are going to use for TE10 mode. So what is TE10 mode? TE10 mode means I am having M as value 1 and N as value 0. So M means number of half cycle toward the broader dimension. So I will write or I will draw it like this. So this is my TE10 mode. So this is my half cycle that is varying along the broader dimension. And here I can say that my value of M is equal to 1 and N is equal to 0. So this thing we are going to perform using our microwave test batch. So this mode we are going to give input to our microwave test batch.
So our aim is to determine frequency and wavelength in a rectangular waveguide working in TE10 mode. So to determine that, we require this lambda g. We have to substitute our values, that is lambda g, lambda c in this equation. That is 1 upon lambda 0 is equal to under root 1 upon lambda g square plus 1 upon lambda c square. Now the question arises, what is this lambda g and lambda c? Lambda, we know that it is a wavelength. But what is this lambda g? So if wave is propagating in a free space, then it will have a different velocity, and that velocity is 3 × 10⁸ meter per second. But once the wave is propagating inside some guided media, the velocity will change. So correspondingly, the wavelength will be called guided wavelength. It will be less than the frequency, it will be less than the wave which is traveling in a free space. So that wavelength is called guided wavelength. And second wavelength, that is called cutoff wavelength, that we will see later. So this is our cutoff wavelength and lambda g is guided wavelength. Now to measure the guided wavelength, we will do experiment. So let me make this in a default mode. So whenever you will start any experiment in this workbench, first of all you have to ensure that all the knobs are at minimum position. So this will be voltage is equal to 0 and current will be 0. Next, we have to ensure that this voltage, whenever you change this voltage should never be greater than 9 volt. Otherwise, it may damage our gun oscillator circuit. So first, we will vary this voltage by using this gun bias, and we'll start varying this, and we'll keep this around 7 volt. So current will be around 0.15 ampere. So I'm changing this. Now voltage is changing. You can see it should be around 7 volt. It should never exceed 9 volt. So let us set this. This is 7.42 volt. Once it is set, the second thing is we have to select mode. Now there are 4 different modes we have already seen. There is audio signal, then continuous wave mode, then we are in PC mode, audio mode, and internal mode. In internal mode, this gun power supply will generate an internally generated rectangular waveform, and this waveform will be transmitted. This will be given to the pin modulator, and pin modulator will modulate and it will transmit. So once this is done, The next thing is, one more thing you can see that I have done all the setting of voltage for gun diode. Then also there is no variation of, there is no signal at the output in an oscilloscope scale. So we have to make one more setting, that we have to give this, we have generated the signal but we have not given this signal to this pin modulator. So in order to give signal to pin modulator, we have to apply this pin bias voltage. Once the pin bias voltage is given to pin modulator, then it will accept the signal and it will start modulating. Right now the pin modulator is not receiving any voltage because we have kept this knob at minimum position. Now I will vary the knob and you can see that once I start varying this knob, it appears that the voltage will, or you can say the rectangular wave will appears in an oscilloscope screen. So our kit is working properly. What we have done is we have given power supply, that is the base bias voltage, to both the diode, gun oscillator as well as pin modulator. Once we have done setting in power supply, the next thing is we want to find out the lambda G. So the lambda G can be found out by using this slotted waveguide section. So we are having a waveguide where we are having this slope. That's why this is called as slotted waveguide section, and we'll measure the distance by using this scale, and we can vary the position of, this is called probe. From the probe we are measuring, we are giving this to oscilloscope. So the probe will detect the signal. We are having detector here. We are having pin demodulator here. Pin diode will be there. It will demodulate the signal, and once again we are getting the same signal that we have transmitted from the gun power supply. Seen in transmission line problem, whenever this load impedance does not equal to the characteristic impedance of line, then the wave which is going in forward direction, these are our traveling wave, and because of mismatch, that is Z0 is not equal to ZL, there will be mismatch in a load, and this whatever voltage going in forward direction will be reflected there. Now there are two traveling wave inside our waveguide or our transmission line. One is going in forward direction and second one is going in backward direction. So these two wave will add at each and every point in a transmission line. So because of this addition, a standing wave kind of a pattern will form along a transmission line. So somewhere it will have a minimum voltage because of the addition. The signal will be out of phase, so there will be subtraction of the signal and there will be minima, and at some location there will be maximum. So when we'll move our probe along the transmission line or our floated line section like this one, we can find out that the voltage level will change in the oscilloscope. So whatever we are receiving, the voltage level at each and every location will be different. And one more thing we have found out in a transmission line, that the distance between two minima or two maxima will be equal to lambda G by 4. So lambda G by 2. The distance between two maxima or minima will be equal to lambda G by 2. So in this practical, what we'll do is we'll move our probe and we'll find out this distance, that is D2 and D1, using this scale. We'll measure scale where we are having a different location of minima. So let us start this. I will move from the end and I will move, or we can do other way around. We can move from left to right, or we can move from right to left, whatever will be there. So I will move from node end towards source. So it will be scale from 6, 7, 8, 9 and so on. So we'll move our probe in a slotted waveguide section, and we'll see the amplitude of this signal which we are receiving. You can see that there is variation in signal, the amplitude is increasing. We want to find out location of two successive minima to find out lambda g. You can see the amplitude are gradually decreasing. Once again, if we starting, it is increasing. So we'll find out the position where the amplitude is minimum. So this is the location where amplitude is minimum. So you can see that when I am moving my probe in a slotted waveguide, so the amplitude of signal is changing at each and every location. At some location, it is, you can see now amplitude is decreasing, and till I am moving this probe, amplitude level is now increasing. It will increase, and once again it will start decreasing till if I will move. You can see the amplitude level start decreasing. Now what we have to do is we will take two positions where our amplitude is minimum. So these are the two locations. We will find out two minima, and from that we can find out lambda g. So we'll see. Let me move from left to right. So I'm moving from left to right, and we'll find out the minimum location. Signal amplitude is decreasing. This once again increasing. So this is the position where I am having a minimum amplitude. So we'll mark this point. This is our can see this is between 13 and 14. Since I am moving along this direction, so this will be my 14 point. This 0 is coinciding at 14.6. And if you want still more precision, then we have to find out where out of this 0 to 10 where we are having this scale where we are coinciding. So we'll take this as a 14.6. This one is our 14.6, and we are moving from left to right. So our scale is changing from 14, 13, 12, 11, and so on. So our first reading will be at this 14.3, and still I am moving in this direction. So next reading will be 13 or 12, whatever it will be. So in our equation we have substituted this d1 is equal to 14.6. Next we want to find out.
Note down these equations and note down the value for d1. Note down the equations as well as note down the value for d1, students. Have you noted?
Yes, ma'am.
The location of second minima, consecutive minima we want to find out. So once again I will move my probe in a slotted waveguide section such a way that we will have a next minima. You can see the signal amplitude is increasing till it is increasing. Now it start decreasing. We'll move further, and this is the location where amplitude is minimum. So we'll mark this point. This is the point. This you can see that once again this is 12.6. We are moving from left to right. So our D2 will be 12.6. So I will write in our equation this D2 will be equal to 12.6 centimeter.
Have you noted this 12.6 value?
Yes, ma'am.
Yes, ma'am.
Yes,
મેમ બંનેમાં મિનિમમ જ છે ને?
બંનેમાં મિનિમમ છે.
D2 will be equal to 12.6 centimeter. Now you have to do this calculation. We have found out D2 and D1. So you have to find out lambda g. You have to substitute D2 and D1 here, and you have to find out lambda g. So this is how we will get lambda g. Still we want lambda c. It is called cutoff wavelength. So cutoff wavelength will be calculated using this equation. That is lambda c is equal to 2ab divided by under root mb square plus na whole square. Already.
So here, what is the value for m? We have already calculated that the value of m is equal to 1. As we are using TE10 in our rectangular waveguide, so we will put m equal to 1. So in this equation, what I will do, I know the value of a already. So what is the value of a? We have already calculated the value of a, that is equal to 2.4 centimeter. We know the value of b. Already we have calculated the value of b, that is equal to 1.1 centimeter. And that is divided by, what is the value of m? M is equal to 1. So we will write them over here 1.1 square. And value of n is equal to 0. So we will keep this n is equal to 0. So the answer is 2 multiplied by 2.4 into 1.1 divided by 1.1. So 1.1 cancel and answer will be 4.8 centimeter. So overall, or I can write down that my lambda c for TE10 mode. Okay, by my lambda c for TE10 mode, what I will write that for TE10 mode, lambda c is equal to 2ab divided by under root of mb square plus na square. So for TE10 mode, what I will write? I will write down the value for m and n. So I will write down value for m equal to 1, that is b square, n equal to 0, so this will become 0. So this equation becomes twice ab divided by b. So for TE10 mode, my lambda c is equal to twice times my broader dimension, and that is what we have calculated, and that value is equal to 2 into 2.4. My answer is 4.8 centimeter. Kindly note down this equation. Note down this equation in your notebook, students. Done?
Yes, ma'am.
yes, ma'am.
Now we find out the value of lambda c. We have already found out. From the slotted section value, we already found out the value of lambda g, that is d1 minus d2, the difference of d1 and d2 multiplied by 2. The answer is 4 centimeter. Make sure the units must be there. Have you calculated lambda g?
Yes, ma'am.
Yes, ma'am.
Okay, so we are putting these values into this equation, and then we are going to find out lambda 0 for our answer, and that answer will be in centimeters. Once we got lambda 0, what we will going to do? We will calculate frequency value. Okay, so frequency is equal to c divided by lambda 0. So this is the frequency which has been generated by the gun oscillator. So this is our microwave frequency which has been generated. So we are going to calculate this frequency, and whatever answer we are getting, we are finding out using the first method.
We'll find out the frequency of
So before going to the second method, calculate the frequency in your notebook. તમારે તમારી frequency notebook ની અંદર calculate કરીને રાખવાની છે. Okay? So calculate it in your notebook અને પછી આપણે આગળ check કરીએ. ત્યાં સુધી આપણે second જે method છે એ check કરી લઈએ. શું છે second method?
Operation by using direct frequency readout meter. This is our direct frequency readout meter. This is your KVT. So this is the KVT. So what we'll do is we have to see this amplitude level. So we will vary the position of so we'll rotate this knob and we can see that this line is going upward. It means it is changing its cavity size. We are changing the size of cavity. So if this cavity will have a resonant frequency, then there will be change in the amplitude level. It will have a change only whenever this cavity will resonate. So at all other frequency we do not have any change in this signal, while at only single frequency where this cavity is resonating, we will notice the change in this amplitude level. So we have to find out that point by rotating this knob in a direct frequency readout meter. So I am slowly changing. You have to constantly watch in this screen. We have to see whether the amplitude is changing or not. So I will rotate this slowly, and at one location the amplitude variation will be there, and that location is our resonant frequency. I am slowly changing it. You can see at this location we are having change in amplitude level. All other location we do not have any change, but at this location there is change in location. So we'll find out this is the resonant frequency of this cavity meter, or you can say this is where the resonance will take place. So in order to find out the frequency, you can see there is one vertical line, red color line, and there are two horizontal lines. This is the vertical line and there are two horizontal lines. So we have to see in between these two horizontal lines and this vertical line where they are intersecting. So we can see that it is around, there are 2 point, one is 10.05 and 09. So 10.0, so you can see that the division is of 0.02 and this point corresponds to 10.09. So this is our frequency which we have calculated using direct readout frequency meter.
So using frequency meter, what we get? We get the value as 10.09 and the unit is gigahertz. Right? So this value we are going to use in our observation table. So we'll use one observation table, and in this observation table we are going to calculate the cutoff frequency using the direct measurement. That means using this value. So we are putting this value over here as it is 10.09 gigahertz, and using the slotted waveguide means whatever the calculation we have done using this, whatever the answer we are getting using this. So on that basis we are going to calculate the frequency, and that frequency we are going to write it over here. So calculate it right now, students. What is your answer? You have to give me your answer. Calculate it right now.
9.87.
What? 9
Hello.
point? Yes.
9.76.
9.7 gigahertz.
9.7 gigahertz. Okay, one answer I got 9.7 gigahertz. What about others?
9.9.
Ma'am,
9.7 gigahertz.
9.2 gigahertz, ma'am. 9.2 gigahertz.
Ma'am, 9.7.
Okay, maximum answers, I think maximum of the students got 9.7. Any other answers other than 9.7?
9.87.
9.87. Okay, any other answers?
9.2.
9.2. Okay. Any other answers?
9.25.
9.25. Okay. Any other answers? Any other answer? બીજા કોઈને હજી કોઈ બીજા કઈ વેરિયેબલ આન્સર આવતા હોય? One I got 9.7, one I got 9.8, one I got 9.2. Any other answer?
9.
Yes.
9.76.
9.76. Okay. After after 2 digits of the point, it's okay. It is nearby 9.7. Any other answers other than 9? Does any one of you got 13 or 2, 3 or any other? I want you to write your answers in the chat box. I want you students to write your answers in the chat box. Whatever answer you got, please write it in the chat box. Please write it, students. Whatever you have, tell me, just please write down in the chat box. Okay, 9.7, 9.8, 9.25, 9.21. Yes. 9.7, 9.76, 7678, 9.8. Okay. Yes. Other, regarding others? Any other? કોઈને બાકી છે calculation? Okay, 9.7. બીજા કોઈને બાકી છે calculation? 9.69. Okay. (9.7), 9.7. Maximum answers are 9.7. 9.8. Okay. Yes. Any other answers? (9.7) again. Okay. Good. 9.9. Okay. 9.62. Okay, good. Any other? Any other answers other than 9? 9.7. Okay, good. Any other answers, students? (9.865). Okay. And what will be the unit? What will be the unit? You have written 9.8 gigahertz. Good. Unit will be in gigahertz. Good. Okay. Now again I am playing my video. જે કોઈ પણ બાકી રહી ગયા છે calculation માં, please write it in the chat box. Okay, I am playing the video. Next. And you have to compare whether these two frequencies are same or not. But what you found that your frequencies are not same. તમને શું જોવા મળ્યું? તમારે બધાના આન્સર્સ કેવા હતા? નિયર બાય 9.7, 9.6, 9.2, 9.9. Okay, તમારા બધાના આન્સર્સ are not exactly equal to 10.09 gigahertz. Okay, આ comparison તમે જો કરી, તમે એક waveguide થી પણ find out કર્યું અને તમે direct measurement માંથી પણ find out કર્યું, but your answers are not same. Okay. So after writing the observation table, you have to give the conclusion of this experiment, whatever you have studied inside this experiment. So you have to write down the conclusions and thereafter your experiment is over. Thank you. So once your experiment is over, okay, what thing you have to write in conclusion? Which thing you have to write in conclusion? So conclusion માં તમને એક વસ્તુ જોવા મળી કે your direct measurement value and using the slotted waveguide section value frequencies are not same. Now can anyone tell me why the frequencies are not same using the direct measurement as well as using the slotted waveguide? Though the micro test bench is same, but why we are not getting same answers? Can anyone tell me? Huh?
મેમ આપણે બે મિનિમાસ વચ્ચે ફાઇન્ડ કરેલા બટ મિનિમા આપણે લીધા એ સાઇન વેવ ના છે તો એક્ઝેક્ટલી પરફેક્ટ નથી.
Exactly true. Yes, I'm again explaining to all of you. I'm sharing my paint with you. Wait a moment, I'm sharing it. So this is our sinusoidal signal. Okay, this is what we are finding out in the slotted section. We at some position we are finding out the minimas occurs, at some position we find out the maximas occurs. Okay, so because of that, what we found out, we have found out the distance between the two minimas. So I am having two sinusoidal signals occurring. So this is occurring inside a waveguide. So over here, what we found, we have calculated the distance between two minimas. This, we represent this as D1 and we represent this as D2. And we have calculated D1 and D2. We have measured the D1 and D2. But while performing the experiment, what we have seen that we have not precisely measured this maximum negative peak. We have not precisely measured the maximum negative peak at D2 distance. We may have calculated, say, at this point also. We may have calculated at this point also. Okay, so we have not taken the precision in this. And because of not taking the precise value, minima value during the experiment performance at that time, so D1 and D2 are varying along the values. અહીંયા જે આપણે જે પરફેક્ટલી જે નેગેટિવ પીક આવી જોઈએ, પરફેક્ટલી નેગેટિવ પીક ઉપર આપણે મેઝરમેન્ટ નથી લીધું, આપણે એની આજુબાજુના મેઝરમેન્ટ લીધા. કા આ લીધું હશે, કા આ લીધું હશે. અહીંયા પણ કા D1 D2 આ પોઈન્ટ ઉપર લીધું હશે, કા આ પોઈન્ટ ઉપર લીધું હશે. આપણે પરફેક્ટલી નથી લીધું અને એના કારણે શું થાય છે તો કે એના કારણે જે અહીંયા ને અહીંયા બે વચ્ચેનો ફેઝ ડિફરન્સ જોવા મળે છે. એ ફેઝ ડિફરન્સ હોવાના કારણે તમને સ્લોટેડ વેવગાઇડની અંદર જે તમે મેઝર કરો છો એ મેઝરમેન્ટની વેલ્યુ કઈ તો કે ફ્રીક્વન્સીની વેલ્યુ ડાયરેક્ટ મેઝરમેન્ટ ફ્રીક્વન્સી વેલ્યુ જેવી આવતી નથી. આ મેઇન રીઝન છે. સમજાય છે સ્ટુડન્ટ્સ હું જે કહું છું એ?
Yes ma'am.
Yes,
Okay,
ma'am.
so because of that D1 અને D2 પ્યોરલી એટલે પરફેક્ટલી આપણે નથી લીધા. જો આપણે કદાચ ધીમે ધીમે શાંતિથી વ્યવસ્થિત કરીએ, પરફેક્શન સાઈડ જઈએ તો આપણને જે આન્સર આવે છે એ નિયર બાય આન્સર આવશે, એકદમ નિયર બાય. We may get near by 10 or we may get near by 9.99 answer. Okay, તો આપણને એ ટાઈપનો આન્સર્સ આવે. બટ ઓવર હિયર we are nearby to our answers. આપણે આન્સર્સની નજીક છીએ. ઓકે, ધીસ ઇઝ ધ રીઝન. અને એ તમારે કન્ક્લુઝનમાં લખવાનું છે કે આ એક્સપેરિમેન્ટમાંથી તમને સ્લોટેડ વેવગાઇડની ફ્રીક્વન્સી જે મળી છે અને ડાયરેક્ટ મેઝરમેન્ટમાંથી જે ફ્રીક્વન્સી મળી છે એ સેમ જોવા નથી મળતી, બટ નિયર બાય જોવા મળે છે. એનું કારણ શું તો કે કારણ જે મેં તમને હમણાં સમજાવ્યું એ. ધેટ ઇઝ ધ ફર્સ્ટ થિંગ. સેકન્ડ કન્ક્લુઝનમાં તમારે શું આવશે તો કે તમે બધાએ સાચા આન્સર્સ આપ્યા છે. 9.8, 9.6, 9.9 તમારા બધાના કેલ્ક્યુલેશન્સ પ્રમાણે. અને આ જ આન્સર તમને જે આવ્યા છે એ જ આન્સર્સ લખજો તમારી મેન્યુઅલની અંદર. ઓકે, એવું લાગે તો તમે 2-3 વાર ફરીથી કેલ્ક્યુલેટ કરજો, પણ જે આન્સર્સ તમારે આવે છે એ જ લખજો, બાજુવાળાના ના લખતા. બાજુવાળા આઈ મીન ટુ સે કે તમારા ફ્રેન્ડ્સના ના લખતા. ઓકે, સો જે તમને આન્સર્સ આવ્યા છે એ જ તમારે લખવાના છે. બીજું તમને બધાને 9 ની આજુબાજુ જ આન્સર્સ આવ્યા છે. ઘણા સ્ટુડન્ટ્સ એવા હતા, મેં જે ગઈકાલે જે લેબ પરફોર્મ કરી એમાં સ્ટુડન્ટ્સ એવા હતા કે સમ ઓફ ધ સ્ટુડન્ટ્સ ગોટ આન્સર એઝ 2 ગીગાહર્ટ્ઝ, some of them got answer as 13 gigahertz, but this is totally wrong. If you are getting answer nearby 2 gigahertz or 13 gigahertz or 6 gigahertz, then that answer is wrong. શું કામ એને રોંગ છે? કારણ કે આપણી માઇક્રોવેવ ટેસ્ટ બેન્ચ જે આપણે યુઝ કરી રહ્યા છીએ આપણી લેબોરેટરીની અંદર, that microwave test bench is working on X band frequency. જે માઇક્રોવેવ ટેસ્ટ બેન્ચ આપણે યુઝ કરીએ છીએ કઈ છે તો કે એક્સ બેન્ડ ફ્રીક્વન્સી ઉપર યુઝ કરે છે. This is you working on X band, અને X band કયું છે તો કે 8 to 12 gigahertz. એટલે જે કાંઈ પણ ફ્રીક્વન્સી ગન ઓસિલેટર જનરેટ કરશે એ ઓલવેઝ ઇટ ઇઝ જનરેટિંગ ઇન બિટવીન 8 gigahertz to 12 gigahertz. એટલે જો તમારો આન્સર 8 gigahertz કરતાથી ઓછો આવે તો ટોટલી તમારા કેલ્ક્યુલેશનમાં કંઈક મિસ્ટેક છે, અથવા તો 12 gigahertz થી વધારે આવે તો પણ તમારા કેલ્ક્યુલેશનમાં મિસ્ટેક છે. So this is the second conclusion that you want to observe, or you have observed, that our microwave test bench works on X band, and X band is range in between 8 to 12 gigahertz, and that is what we found out, that my cutoff frequency is using the direct method as 10.09 gigahertz and using the slotted waveguide section as whatever you have calculated. Clear, students?
Yes, ma'am.
Now, कोई ने
Yes.
doubt?